Hello class, we are on section 1.2. We're going to discuss initial value problems. We discussed this quite a bit in our last video, in our first video of this lecture series. I think it might have been a little bit rushed, so maybe you want to go back through there and just kind of review what we talked about a little bit as far as initial value problems go. But we're going to dive deeper into those today. Now, just a reminder, the video series is meant to be watched just like you would read a math textbook, and that is with a pencil and paper. Okay, so whenever you read a math book, you should have a pencil and paper with you. You should be writing a lot of stuff. As you go through these videos, you should also have a paper and a pencil with you, because I will stop and pause at certain times through certain videos and say, hey, try this on your own now, and now check your answer versus the solution we're going to have, right? So just a reminder, it's always good to kind of work through things and take notes on the videos like you would through a textbook. Okay, so initial value problems, as we said before, the shorthand name for those are IVPs, right? So an IVP is an initial value problem. It's a differential equation that has some sort of initial conditions set, right? Our shorthand for initial conditions is IC, right? So again, an initial value problem means that some sort of initial conditions have been specified for a solution. What this does is it helps us to narrow down to hopefully a single solution. Okay, so generally a solution for a differential equation is an infinite set of functions, okay, that generally vary by some constant multiple, right? So we call that a family of solutions. There's a family of solutions that satisfy our differential equation. So if we set some conditions on the solution we want, it helps us to narrow down to a unique solution is what we call it. Okay, now there's not always a unique solution. Sometimes there is no solution. Sometimes we have to go through other means, which we will talk about in chapter 2. Okay, so it is possible that more than one solution in a family of solutions share the same initial conditions. So what we do is if we have an order n, we need to set initial conditions not just for the function, but for its derivatives up to n minus 1. Okay, so what do I mean by that? I mean that we may have, if all that we do is say, hey, I need my function to satisfy that when I plug 0 into it, I get out 1. There may be several solutions that satisfy that condition, right? So I need to set conditions on the derivative of my function as well at that point of 0, right? I need that if I plug 0 into y prime, that I get out 3. I need that if I plug in 0 into the second derivative, that I get out 12, right? Whatever, up to whatever order I am, 1 less than that, okay? At this initial point that we call x0. Right? So if we can do that, then this will help us to try to identify a unique solution. If we can't find a unique solution, then there's no solution that exists, okay? So that's the condition that we need in order to try to narrow it down to something that's unique, right? So this brings us to a set of questions that we can ask about this statement, okay? So again, we're trying to take a family of solutions and narrow it down to a single solution, okay? So then the question comes about is there even a unique solution, right? Or are there any solutions at all? Okay, so do we have solutions that exist to this differential equation? And if we do have solutions, can we narrow it down to a single solution? So we call this a question of existence and uniqueness, okay? Do there exist solutions, and does there exist a unique solution? Well, luckily it turns out that there is a theorem that helps us to identify when we have solutions that exist and when those solutions are unique, okay? So, again, we refer to this as the question of existence and uniqueness. This is a common question that we ask. So let's go ahead and go over this theorem. So we're going to let R be a rectangular region on the xy plane. So again, the xy plane is just a regular Cartesian system, right? So you guys are all past Calc 3 as you watch this, so you're familiar with the different plane systems in 3 dimensions. So here we're just using the standard 2-dimensional Cartesian coordinate system, right? The X and Y axis. So let's just say that we have a rectangle that we call R. Okay. So this rectangle, this region, it exists from some start to some finish in X and some start to some finish in Y because it's a rectangle, right? So the interval that exists over the X is from A to B, right? X is an element of A to B. So it starts at A and ends at B on the X axis, okay? And it starts at C and ends at D on the Y axis. So it's in some rectangle in space from A to B, and on the up and down portion, the smallest value you can have is C and the largest is D, right? So within this rectangular region, we have a point which we'll call X naught, Y naught. This represents our initial value, right? Our initial conditions. When I plug in X naught into my DE, I get out Y naught, right? If we have a function X in terms of X, Y, and the partial of this function in terms of Y is continuous within this region. So there are no point discontinuities, there are no jump discontinuities. It is a continuous function within this rectangle, okay? And there exists an interval which starts a little bit before X naught, right? A distance of H away, and it ends a little bit further than X naught. So we call this within the neighborhood of X naught, right? So it's a little bit before, it's a little bit above, very similar to the sigma delta notation that you would talk about in terms of limits, right? So if I'm in the neighborhood of this point, here, obviously H is larger than 0, which allows me to be a little bit before, a little bit above, right? Is contained in this interval, and a unique function y of x is defined on this I naught, this interval, right? Then there is a solution to the IVP, y prime equals this function, such that y of x naught is y naught, okay? And here is our image. Okay, so let's discuss this one more time because it's always good to go over deep theorems like this so that they make sense to you. So I have a rectangular region from A to B on X, from C to D on Y, okay? And within this region, there is a neighborhood around some point, okay, which I would like to consider my initial condition, okay? And within this neighborhood, there is going to be a unique function, right? And on this function, it is defined on this interval. Now, this function is unique only if the function that I'm looking at is continuous over this region and its first partial derivative in terms of y is also continuous. So that is my condition. If I have a continuous function over here, over this interval that goes to this point, and its first derivative with respect to y is also continuous over this interval, this region, then within this neighborhood of the point that I'm interested in, I will have a unique solution, okay? And so this is for the first derivative here, okay? And it will satisfy this point that I'm looking at, right? So we will extend this later on to as long as, let's say I had the third derivative, I would need my function and I would need the first derivative to be continuous at that function and the second derivative to be continuous at that point or over this region and have input outputs as well, okay? So let's go ahead and do an example. Let's say that y equals 1 over x squared plus c is a solution to this non-linear first order differential equation, which is homogeneous. We want to find the solution to this initial condition. So obviously you can see here I have x squared plus c on the denominator. So this is a family of solutions, right? So I want this solution to satisfy this condition. So that part is very, very easy. But I also want to find the interval of existence. So that's going to take a little bit more work. So what I want to do is I want to plug in -2 for x, 1/2 for y, and basically just solve for c. Very straightforward, right? So this point, this input-output pair, implies that this is what I have for my setup. And when I solve for c, right, if I multiply by 4 plus c on one side and times 2 on the other, my equation turns into this, right? I'm not going to bore you with the details. You guys are good at math. Subtract 4, and I got c is -2. Now, if you've never seen this symbol, this 3 dots means therefore, and you say it just like you would in a sentence, right? Y of -2 equals 1/2. This arrow means implies, right? So when I plug in -2, I get out 1/2, implies that my equation looks like this, and this implies that this is my setup for c, and when I solve for c, therefore c has to be -2. Okay, so I'm going to use this shorthand notation quite a bit. Hopefully this is semi-familiar to you from your previous instructors, but that's how this class is going to go. Now, I could say that this input-output implies this equation, and then work it vertically like we normally do. However, this is a video and I don't have a lot of space, so I'm going to work horizontally quite often. I do work vertically a lot, but for small calculations like this, I just work it horizontally, come to a conclusion. Okay, so you will see me work in the vertical sense when it makes more sense to do so, right? So therefore, my constant here is -2. I need to know the interval of existence. Okay, so this is my solution to this dE, such that st means such that y of -2 is 1/2. Okay, so this condition gives me this unique solution, right? So this only exists when the denominator is non-zero. Okay, so that means that, well, let's look at this, right? This is basically 1 over x squared. 1 over x squared is a non-continuous function, right? There's a zero, there's a gap at 0. So this is basically shifted, right? This is basically has some sort of a horizontal shift. So when I solve for this, I get x is plus or minus square root of 2, right? So there's 2 portions where it is discontinuous, right? So then that means that this rational function has 3 parts. Okay, it has a left side, it has a middle part in between -√2 to √2, and after √2, because it has 2 vertical asymptotes, right? So it has 3 parts, so I need to choose for my interval of existence the portion that contains this point. Okay, so that means since I'm at -2, my interval of existence is from -infinity to -√2, right? So if I look at the graph of this, there's 3 discontinuous portions because I have 2 vertical asymptotes. This left side, right, is the part that contains this point. So this is the part where my interval of existence is, right? It's not over the other non-continuous, the other continuous portions. It's over this portion, this continuous portion, right? Next example. So we want to find a function y equals f of x whose second derivative is y double prime equals 12x minus 2 at each point x, y on its graph, and y equals -x plus 5 is tangent to the graph at x equals 1. Okay, so these are my conditions. They're giving me a second derivative function. They are giving me a tangent line to the function itself. So we should have enough information to try to find our original function. So obviously, if we have a second derivative and we want to get down to our original function, it makes sense to integrate this thing twice, right? So that's where we'll go ahead and start off. So if I take the first derivative of the function that I want is going to be the integral of this function with respect to x, especially since it's telling me that y is a function of x. So I'll integrate this with respect to x, okay? And I will get 6x squared minus 2x plus c1. Now I'm calling it c1. I could just say c, but I'm calling it c1 because in order to get down to y, I will need to integrate this again, which will give me another constant of integration, which I need to call something else. So since I'm going to have more than one constant, I'm going to differentiate between them by obviously giving them subscripts like we normally do in mathematics, right? So I have a condition on y prime, right, at the input of 1 of getting an output of -1, right? Because this line is tangent to my function at the point of 1, and it has a slope of -1. Okay, so hopefully you remember your calculus 1. That means the rate of change, the instantaneous rate of change, or the slope of the tangent line to my function at this point is this value, right? So y prime of 1 has to be -1. Now I could use this now to try to isolate this function down by plugging 1 in 1 and getting -1 out, and then getting out a value of C1. And that's fine and dandy. There's nothing wrong with that. I'm just not going to do it now. I'm going to save it till later, just to show you how things kind of work in this space, right? So if I want to get down to y, I'm going to just go ahead and integrate my previous output. So this will shoot up to x cubed, and this will become a 2. This will become -x squared, and this will become C1 of x, right? And then I add another constant of integration, okay? So I have the initial condition here that y of 1 equals 4. So now you might say, well, how do you know that? Well, if this is tangent to my original function at this point, that means that they have a shared point, right? So if I plug 1 into here, I'm going to get out 4. So that same point is shared on my original function. So this input in this tangent line gives me a point, and it gives me the slope of the tangent curve. So that gives me a pair of initial conditions here. Okay. So now I can use both of these initial conditions to solve for C1 and C2, right? So again, like I said, I could have done this right away, or I can leave it to the end. There's really no difference in the timing. So when I plug in 1, I just get 6 -2, right? Plus my constant, and that equals -1. So that gives me C1 is -5, right? So now that I have this, I can plug that into what I have here, right? I could have done it from the beginning and had -5x, right? And then plugged in my initial condition. Again, the order doesn't really matter, okay? Most of the time, however, you're not going to be able to do this until the very end, so that's why I waited till the end for you guys. So when I plug in 1 to my function, right, with the C1 and C2s, I'm going to have 2, right, because I'm plugging in 1, -1. This is now -5 plus my constant that I'm trying to solve for. So I combine these together, and I basically get what? 2 minus 6 is a -4, so I get C2 is 8. Okay. I am not done, however. Okay, it's very common for students in mathematics to get to some sort of result and say that they're finished. I'm not done, right? The reason I'm not done is because I have not explicitly written out my function yet. So I got to make sure I write my answer, right? So since C1 is -5 and C2 is 8, my final solution is this function of y. Okay. Now, if I really wanted to check to see if I was correct, well, I would take the first derivative here and find its slope at 1. Okay. I would take the second derivative and see if it comes out to this function, right? I would just work myself backwards, which is fine. This is basic calculus 1, calculus 2 stuff. So you should be pretty confident in your answer here. Okay. So let's do another example. Right, so this is coming from our theorem about existence and uniqueness. We want to determine a region in the xy plane such that this differential equation has a unique solution whose graph passes through a point x0, y0 in the region. Okay, so if I take y0 minus y equals x, so let's go back to our theorem that we had way back here. Okay, so it's saying that if this is my solution, okay, I need a function whose continuous and its partial in terms of y is continuous as well. If you notice here, my function is y prime equals f of xy. Okay, so I have y prime on one side and my f of xy on the other side. It says that this f of xy needs to be continuous on R, the region, and its first partial in terms of y needs to be continuous over this region as well. And if that is true, then I can have a function y that satisfies these conditions and is the solution to this dE, right? So y is the solution. F of x is the equation that my derivative is equal to. So I need to take put everything on the right hand side except for my derivative. Okay, check to make sure that that function is continuous over whatever region has been specified. Okay, and that its first partial is also continuous over that region. That is what we are doing for this next example. Okay, so here's my dE, right? I need to determine if there is a unique solution to this or not over an unspecified region. So that really just means over R, or what that region would be, in fact, right? I'm trying to actually narrow down the region. So we're going to move everything over to one side. So this should be y prime equals x plus y. Okay. And now I'm going to look at the region that this thing is continuous on, right? Because this is my f of xy function, right? It's a function in x and y. And this is continuous everywhere. There's no restrictions here. There's no square roots. There's no rational functions. There's no natural logs. There's nothing here that has restricted domain, right? X and y, their open domain is continuous over all of R. Okay. So now I need to look at its first derivative of this y plus x function. Okay, so again, some more notation here. This upside down a means for all. Okay, this function is continuous for every x value that exists in R. This is continuous over all of R. All right, there's no values of x that I cannot plug in, no values of y I can't plug in. It's continuous over all real numbers. Okay, remember, y is a function of x. There's nothing I can't plug in here. Okay. I need to find the first derivative of this function with respect to y. So again, we're basically holding x as a constant, so that goes away when I differentiate, and y goes to 1. This is also continuous over all of R as well. Okay, so both of these, the f of xy and the first derivative of f of xy, are both continuous over the entire space. So again, let's come back over here to our definition. The function that I have when I set the derivative of y equal to everything else and the first derivative. For my example, they're continuous, they're overlapping domains is that region that I'm specifying. Okay, so their overlapping domains in this case is all of R. So this will have a unique solution over all of R. Okay, so therefore that function y plus x and its first partial with respect to y are continuous over the same interval. Therefore there exists a unique solution which we call y of x over any choice of point x naught, y naught in the xy plane. Okay. So let's do another example. So consider y prime equals x minus 2y such that when I plug in 0, I get out 1/2, right? So which of the two curves is the only plausible solution curve? So here's a perfect example where I have two functions, okay, that satisfy the same initial condition. Okay, so there's two possible solutions. In this case, there's probably more than that, and they both satisfy this initial condition. So only one of these actually works here, right? So let's think about this. What is a derivative? A derivative talks about your rate of change. I have an input and an output, so let's plug those into my function. Okay, if I plug in 0 for x and 1/2 for y, I get out -1. So the only function that makes sense here is the one that has a negative rate of change, or is the decreasing function, right? So therefore the decreasing function at x is 0 is the correct function. Okay, see you guys on the next one. Thanks.